Picture a future far ahead of our own, one where humanity has worked through its present struggles and finally pushed outward, leaving this small planet behind to make a home among the stars. Given enough time, our descendants spread across the whole of the Milky Way, countless trillions of people living together in peace, stretching from the crowded core of the galaxy out to its farthest, loneliest spiral arm. Then, one day, a signal arrives from somewhere else entirely, sent from another galaxy, another cluster far beyond our own. It turns out, we are not alone. Another form of intelligent life exists out there in the cosmos. Contact leads to an exchange of ideas, and knowledge flows both ways. Science, art, and philosophy all flourish as a result. Eventually, ambitions grow bigger. Out in the emptiness between galaxies, the two civilizations decide they want to meet in person. Building a vessel capable of covering that kind of distance takes the combined effort of many generations. And many more generations are born, live out their entire lives, and die before the journey is even finished. But after thousands upon thousands of years, drifting through that black, starless gap, representatives of both civilizations finally draw close to one another. Two figures drift out into the void between the ships, arms outstretched, reaching for each other. Their hands meet, and in that instant, both disappear in a flash of blinding light. The two great vessels pull back, their crews staring in stunned disbelief. It turns out the two civilizations were built on something fundamentally incompatible. Only now does it become clear that one side was made of ordinary matter and the other of antimatter, and that any contact between the two could only end in mutual destruction. Both ships withdraw into the darkness, understanding at last that genuine contact between them was never going to be possible. So how did things end up this way? How could two advanced civilizations fail to notice something so basic about their own composition? They had exchanged knowledge of science, mathematics, and engineering with one another. Surely a difference this fundamental should have shown up somewhere along the way. But anyone with a deeper understanding of physics would know better. Nature is famously reluctant to give up its secrets. Built into the very laws that govern the universe are rules that keep certain truths hidden from casual observation. These are not minor technicalities, but principles woven into how the universe itself operates, showing up in processes ranging from the scale of galaxy clusters right down to the subatomic. These same rules played a role in shaping reality during the very first fraction of a second after the universe began, in that first billionth of a second when everything was still taking form. And running underneath every one of these rules is a single unifying idea: symmetry. Think about it this way. Two separate civilizations, living in completely different corners of the universe, would still be governed by the exact same laws of physics. So how could they possibly have missed something as basic as the distinction between matter and antimatter? We're talking about particles, atoms, even living beings that differ only in the sign of their electric charge. In our corner of the universe, ordinary matter is everywhere, and antimatter is scarce. In their part of the cosmos, it must have been the other way around. We orbit a star made of matter. They lived under the light of stars made of antimatter. Our spacecraft are built from atoms, theirs from anti-atoms. It's tempting to assume that the laws of physics simply don't distinguish between matter and antimatter at all, treating them as perfect mirror images with no meaningful difference. But that assumption turns out to be wrong. Physics actually does treat matter and antimatter a little differently, in ways that are subtle, unexpected, and tied to one of the most profound ideas in the entire field: symmetry. So what exactly do we mean by symmetry? Most of us first encounter the concept through a mirror, seeing how our reflection flips left to right. Give a child a small mirror, and they can trace out a symmetrical shape easily enough, where anything drawn on one side has a matching partner on the other. But that simple mirror trick points to something that runs much deeper through the natural world. Our own faces and bodies are built along these lines, a right eye paired with a left arm balancing a right. This kind of mirror symmetry, sometimes called bilateral symmetry, shows up again and again across the animal kingdom, in mammals, reptiles, birds, and fish alike. When that pattern gets disrupted, the results can look strange to us. Think of the fiddler crab and its one oversized claw, completely out of proportion with the other side of its body. But symmetry isn't limited to simple mirroring. A starfish is built around rotational symmetry, meaning it looks the same no matter how you turn it. A millipede relies on translational symmetry instead, assembling its long body out of repeating identical segments. In each case, nature is essentially taking a shortcut, using symmetry as an efficient way to build complex structures. Symmetry also seems to trigger something emotional in us. We tend to find symmetrical faces and forms more attractive, even though that kind of beauty really is only skin deep, since our insides are famously lopsided and irregular. That instinctive appreciation for symmetry shows up throughout human art and architecture. The ancient temples of Egypt and Greece display striking symmetrical design, and the same holds true for more recent landmarks like the Taj Mahal and the Arc de Triomphe, along with countless works of art, including Leonardo da Vinci's Last Supper. Artists and architects haven't limited themselves to plain mirror symmetry either. Rotational symmetry has its own kind of power, visible in the spinning stone discs left behind by pre-Columbian civilizations in the Americas, and in the intricate geometric patterns decorating mosques across the world. Even the massive headquarters of the United States Department of Defense carries its own geometry right there in its name, built in the shape of a pentagon. Symmetry really does turn up everywhere you look. But you might still be wondering what any of this has to do with the deep underlying rules of the universe. Well, that particular story actually begins with a duel. Early in the morning on the 30th of May, 1832, two men faced off in a field just outside Paris. Nobody's entirely sure what sparked the fight, though according to rumor it had something to do with a woman's affections. By the time the sun had fully risen that day, a 20-year-old mathematician named Évariste Galois lay dying in the grass. The night before the duel, Galois seemed to have sensed that his death was coming. Working through the early hours of the morning, he wrote out a series of letters to friends and fellow mathematicians, and packed into those letters were the last of his mathematical ideas. Despite living such a short life, Galois had already introduced a number of genuinely new concepts to mathematics, and right at the heart of his work was the idea of symmetry. The mathematics of symmetry itself wasn't something Galois invented from scratch. Geometers going back to antiquity had already noticed that rotating a circle leaves it looking exactly the same, and that shapes like triangles, squares, and pentagons return to their original appearance after being turned through specific angles. Galois, though, pushed the idea much further. His real interest was algebra, and specifically the behavior of polynomials, which are simply equations built from quantities raised to different powers, squares, cubes, and beyond. A basic example would be something like 1 plus x squared. A more complicated one might look like 3 plus 5 times x raised to the 5th power minus x raised to the 7th power. Polynomials like these show up constantly, not just in pure mathematics, but throughout science, engineering, economics, and plenty of other fields. Mathematicians before Galois had spent a great deal of effort trying to find general algebraic formulas for solving higher-order polynomial equations. Galois took things a step further and asked whether a single, universal formula might exist, one equation capable of solving every polynomial equation there was. Instead of finding that ultimate formula, though, he proved that the whole search was doomed from the start, since no such general solution actually exists for polynomials beyond a certain degree. And he didn't arrive at that conclusion by grinding through pages of algebra. He got there by studying the symmetry of the solutions themselves. Galois recognized that the solutions to these polynomial equations were complex numbers, and that each one corresponded to a specific point on what mathematicians call the complex plane, an infinite, two-dimensional space. Plotted together, these points could trace out recognizable shapes, sometimes triangles, sometimes pentagons, sometimes other geometric forms entirely. And any shape, of course, comes with its own symmetries, ways it can be reflected or rotated and still look the same. This was a genuinely new way of approaching mathematics, translating abstract equations into visual, geometric terms, and then examining their symmetrical properties. In the years since Galois did this groundbreaking work in the early 1800s, Mathematical thinking about symmetry has expanded enormously, eventually developing into an entire branch of mathematics known as group theory, the study of collections of objects that share common properties and symmetrical structures. Group theory quietly runs the machinery behind modern code-making, but its reach into symmetry has done something far bigger than protect secrets. It has reshaped how we understand the cosmos itself. And there's a strange poetry in this. As Galois lay dying, bleeding out from a duel in the early morning light, he had no idea that the frantic notes he'd scrawled the night before would eventually help crack open the structure of the universe. Long before any encounter took place, two civilizations separated by staggering distances began exchanging signals. Radio beams crossed the void, each transmission taking millions of years just to arrive. It was an agonizingly slow form of conversation, but it worked. Both sides understood the same physics of electromagnetism. Here on Earth, our messages rode on the jostling motion of electrons packed into a radio beam. On the receiving end, in whatever instruments the aliens used, charged particles jittered in response as the signal rolled in. Except their particles weren't electrons at all. They were the antimatter twin, positrons, swaying in rhythm with the same radio waves. Here's the catch. Electromagnetism carries a deep symmetry within it. Flip every positive charge to negative, and every negative to positive, and nothing about the physics changes. As scientific thinking gradually pushed aside mystical explanations, mathematics revealed symmetrical patterns hiding inside physical laws. The spherical pole of Newtonian gravity, for instance, explains why planets and stars end up round. Meanwhile, the magnetic field surrounding a current-carrying wire takes on a cylindrical shape. These are geometric symmetries, satisfying to look at, sure, but they only scratch the surface. Underneath them lay something far more profound, symmetries buried not in shape, but in the mathematics governing the universe itself. Many scientists contributed pieces to this puzzle, but the story really centers on two figures. One was Giuseppe Lodovico Lagrangia, an Italian-born mathematician better remembered by his French name, Joseph Louis Lagrange. The other was the Irish mathematician William Rowan Hamilton. Their lives had almost nothing in common. Lagrange lived through the upheaval of the French Revolution and helped establish the metric system, while Hamilton, nearly a century later, was something of a child prodigy growing up in Dublin. Yet despite the gap in time and circumstance, their work converged on the same target, rebuilding Newton's equations from the ground up. The key insight both men leaned on was this strange notion of least action, the idea that nature always follows the path requiring the smallest possible effort. That concept actually traces back even earlier to the French mathematician Pierre de Fermat, who proposed that light always takes the fastest possible route through any given medium. Picture yourself standing on a beach, waves rolling in. Out in the distance, off to your left, you spot movement in the water. Someone waving. No, wait, someone's drowning. You need to reach them immediately. But what's the fastest way there? You can sprint across the sand, but you're much slower once you hit the water. Running straight toward the shoreline before cutting out to swim would waste precious time. Maybe you should hug the beach as long as possible and minimize the swimming distance. As you run the numbers in your head mid-sprint, you realize there's a smarter route. Some ideal balance between running along the sand and cutting diagonally into the surf gets you there in the shortest possible time. Every other path takes longer. That's essentially what Fermat noticed about light. It behaves exactly like you racing to a swimmer in trouble, always finding the route that takes the least time between 2 points. The way light bends when it passes from air into water mirrors the bent path you'd take running from sand into sea. But Fermat's insight applied only to light. Lagrange and Hamilton wondered whether this same logic might stretch across the whole of physics. And remarkably, buried inside their equations, they found exactly that. Nature, across the board, always seems to pick the laziest available option. It's a genuinely puzzling fact. Why should the universe behave this way? Nobody has a definitive answer, but the principle simply holds up, again and again. To formalize this, physicists calculate something called the action for any physical process, Then compare it across every conceivable way that process might unfold. Take light traveling between 2 points. There are infinitely many hypothetical paths it could follow, and each one has its own associated action value. Nature, it turns out, always selects the path where that action is at its smallest. This holds true from Newtonian mechanics to Maxwell's electromagnetism, from quantum theory all the way through Einstein's general relativity. The universe's laziness shows up everywhere. This principle of least action gets expressed in precise mathematical form, and it was exactly this mathematics that caught Emmy Noether's attention, leading her to a striking realization. She found that whenever these equations displayed a symmetry, that symmetry guaranteed the existence of some quantity that stayed constant, unchanging no matter what. This became one of the cornerstones of modern physics, the concept of conserved quantities, amounts that simply never change. The most familiar example is probably energy conservation. Most of us learn early on that energy can never be created or destroyed, only converted from one form into another. Toss a ball upward and the energy you put in shifts between kinetic and potential as it rises and falls. Light a fire and the chemical energy stored in the fuel converts precisely into the heat and light released. But that's really just the starting point. Conserved quantities show up constantly throughout physics. In particle interactions, whenever a positive electric charge appears or vanishes, an equal and opposite negative charge appears or vanishes alongside it. Across the whole universe, total electric charge nets out to a tidy zero. Similarly, when two objects collide, the total momentum involved stays fixed. Whatever momentum existed right before impact exactly matches the momentum measured right after. Once again, the universe maintains this quiet balance. So why do certain quantities behave this way while others like mass, speed, acceleration, or temperature don't get the same treatment? What separates the conserved quantities from everything else? Emmy Noether's answer was symmetry. Imagine setting up some physics experiment on a tabletop, maybe a collection of springs and bouncing balls. You run the experiment and carefully record how everything moves and interacts. Now you shift the entire table 10 meters to the left and run the exact same experiment again. Naturally, relocating the table changes nothing about the results. The springs stretch the same way, the balls bounce identically. The underlying physics doesn't care where in space the experiment happens. That consistency is itself a symmetry, one physicists call translational symmetry. For Noether, spotting that hidden symmetry meant something else had to be true. Some quantity had to stay fixed, untouched by the passage of change. Working through the mathematics behind the principle of least action, that elegant idea of a universe that always takes the lazy path, she demonstrated that the quantity preserved by this particular symmetry was nothing other than linear momentum, the combined product of mass and velocity across a system. In other words, symmetry under translation in space guarantees that momentum is conserved. But that was just one thread in a much larger tapestry. Buried within the equations were further symmetries, and each one pointed to its own conserved quantity. Perhaps the most astonishing case involves symmetry across time itself. If you ran an experiment today and then ran it again tomorrow, the outcome should be identical. That invariance, that sameness across different moments, produces what might be physics' most celebrated conservation law of all, the conservation of energy, born directly from time symmetry. What Emmy Noether uncovered was a conclusion so powerful it is held up to a century of scrutiny and testing. Every single conserved quantity found anywhere in the universe can be traced back to some symmetry lurking underneath it, and every symmetry, in turn, guarantees a corresponding conservation law. These connections are not always obvious. Many are tucked deep inside the mathematics of quantum theory, hidden and subtle, yet their consequences ripple outward in profound ways. Quantum mechanics describes the world through waves, and these waves behave a bit like ripples spreading across the surface of a pond. The crucial difference is that quantum waves are not made of water or any physical substance. They are waves of probability. Even so, they share several features with ordinary water waves. Just as a water wave has a wavelength describing its length, a quantum wave has an amplitude describing its strength. And just like water waves, quantum waves carry something called phase, which tells you where in its oscillation cycle the wave currently sits. Is it riding a crest or dipping through a trough? The key insight: the measurable properties of something like an electron do not depend on the phase of its wave function. You can shift that phase however you like, and nothing physical about the electron changes. This particular symmetry, the invariance under phase shifts, is precisely what gives rise to the conservation of electric charge. The deeper you dig into the mathematics of quantum theory, the more of these conservation laws surface, and some of them describe rather exotic quantities. There is baryon number, lepton number, isospin, and strangeness, just to name a handful. Some symmetries go even further, actually predicting the existence of fundamental forces. Gauge symmetries, for instance, give rise to gauge bosons, including the gluons responsible for binding protons and neutrons together through the strong nuclear force. That force itself emerges from a deep symmetry between protons and neutrons, an underlying similarity between the two that quantum mechanics translates into a physical interaction. So when physicists sift through the chaotic debris of particle collisions inside the Large Hadron Collider, it is these very conservation laws, rooted in quantum symmetry, that quietly govern everything happening in the wreckage. Given all this, you might expect every fundamental interaction in nature to be completely bound by these rules, symmetry and conservation working together like two sides of the same coin, everything perfectly balanced. And for the most part, that expectation holds true, but not entirely. There are exceptions to this rule, and as it turns out, those very exceptions may be responsible for shaping. Around the middle of the 20th century, astronomers had extraterrestrial life on their minds. Massive radio telescopes swept the sky, straining to catch even the faintest signal from some distant civilization. Some scientists debated what humanity would even say if that first contact ever happened. But others were preoccupied with a stranger and more fundamental puzzle, one involving the possible existence of beings made entirely of antimatter. At the heart of that puzzle was something surprisingly basic. How do you distinguish left from right? It sounds like a trivial question, but it turns out to be deeply entangled with the difference between matter and antimatter, and with the fate of any civilization built from one or the other. Try explaining to an alien what left and right actually mean. It is far trickier than it first appears. You cannot simply send a picture, because interpreting the image correctly would already require knowing which side is which. You cannot rely on cultural conventions like writing systems either, since those need the same reference point to make sense. What you actually need is some feature baked into the fundamental laws of physics itself, some built-in asymmetry that breaks the tie between left and right. And that search leads straight into the concept known as parity. In 1956, that symmetry cracked. In a laboratory in the American capital, individual cobalt atoms were spinning inside a magnetic field. The physicist running the experiment, Chien-Shiung Wu, was watching closely, waiting for the cobalt nuclei to undergo radioactive decay and release electrons. By cooling the cobalt atoms and aligning them within the magnetic field, she made sure they were all spinning in the same direction, which let her track exactly which way the emitted electrons flew. According to the conservation of angular momentum, those electrons should have shot outward evenly from both poles of the spinning cobalt, some heading out from the North Pole, an equal number escaping from the South. But as Wu tallied the results, something strange emerged. Rather than splitting evenly between North and South, nearly all the electrons seemed to be flying out from just one side of the cobalt atoms. The decay process was clearly not behaving symmetrically at all. What did that actually mean, though? Why would it matter if cobalt atoms had a preference for spitting electrons out one particular way rather than the other? The answer comes down to that concept of parity. Before the 1950s, physicists generally treated the conservation of parity as an unshakable pillar of physics. It implied that whatever you would observe in some hypothetical mirror image universe would be just as physically valid as what we observe in our own. Picture an atom. When one of its electrons drops from a higher energy level down to a lower one, it releases a photon of light. Which direction does that photon travel? On average, you would find half the photons heading off to the right and the other half heading left. Now imagine looking at that same atom reflected in a mirror. The mirror swaps left for right, but it also reverses the sense of spin, flipping clockwise rotation into anti-clockwise and vice versa. So in the mirrored version, you would still see half the photons going left and half going right, with angular momentum still perfectly balanced overall. That means the emission of light, an electromagnetic process, respects parity conservation. Gravity behaves the same way. Picture a planet spinning and orbiting its star in a clockwise direction. Flip that into the mirror universe, and everything simply becomes anti-clockwise instead, with no contradiction. At the quantum scale, there is another force worth examining. Inside every proton and neutron, quarks interact with other quarks by trading tiny particles called gluons. This exchange is the strong nuclear force at work, the very force holding atomic nuclei together. Both electromagnetism and the strong force play by the rules of quantum symmetry and its associated conservation laws. Then there is the fourth fundamental force, the weak nuclear force, and it behaves quite differently from the rest. It governs certain radioactive processes, transforming neutrons into protons while ejecting electrons in the process. Because radioactive decay is not something we encounter constantly throughout the cosmos, the weak force had long been treated as something of a minor player among the fundamental forces. That reputation changed abruptly in 1955, when physicists realized the weak force was far stranger than anyone had assumed. Particle physics had been thriving throughout the early decades of the 20th century. Wave after wave of newly discovered particles and quantum revelations kept peeling back the hidden layers of the subatomic world. As recognizable patterns started forming among these particle families, the behavior of the weak force gradually came into sharper focus. Two physicists, Chen-Ning Yang and Sung-Dao Lee, stood right at the center of that effort. As young researchers working at Princeton, they set out to make sense of what recent nuclear experiments had actually revealed. Physicists already understood that the weak force sat behind certain kinds of radioactive decay, and that inside those decays, the brilliant Wolfgang Pauli had proposed something almost ghost-like must be flying away unseen, a new particle called the neutrino. Nobody had ever detected one directly, but the principle of energy conservation was untouchable, so the particle had to be real, whether anyone could catch it or not. Yang and Lee found themselves staring at a genuine puzzle. Every fundamental force they knew of respected something called parity, essentially the idea that nature shouldn't care whether you're looking at a process directly or through a mirror. Yet nobody had actually confirmed that the weak force played by that same rule. Nobody had proven it. And out of that gap came a bold hunch. What if the weak force simply didn't bother with parity? What if it behaved differently when reflected, as though a mirror version of our universe would actually function in a different way? It was a striking notion on paper, but ideas like that need proof. Someone had to design an experiment capable of showing whether the weak force genuinely broke the mirror symmetry of the universe. That's exactly why Wu chilled her cobalt atoms down and surrounded them with a magnetic field. Think about how a photon leaves an excited atom. Electrons being ejected from a radioactive nucleus should, in principle, spin either clockwise or counterclockwise with equal likelihood, meaning they should shoot outward toward the north and south poles in equal numbers. But that isn't what showed up in Wu's careful measurements. So why would the electrons overwhelmingly come out of just one end of a spinning cobalt nucleus rather than spreading evenly? The answer turned out to be extraordinary. Pauli's neutrino, it seemed, could only spin in one direction relative to the way it moves. Only clockwise neutrinos exist. Because angular momentum has to be conserved, those neutrinos can only be released from one particular pole of the nucleus, forcing the electron to exit from the opposite end. Flip that neutrino in a mirror, and you'd get one spinning counterclockwise, but nature simply doesn't produce that version. It doesn't exist here. Which means the mirror image version of the weak force has no place in our universe. The weak force breaks parity, plain and simple. This finding earned Yang and Lee the Nobel Prize for Physics in 1957, one of the quickest turnarounds the Nobel Committee has ever given in the field, especially compared to the 17 years Einstein had to wait for his own recognition. Strangely, Wu wasn't included in that prize, yet her name remains permanently tied to the experiment that rattled the foundations of physics. What this really tells us is that neutrinos can distinguish left from right, and by extension, so can the fabric of the universe itself. But this was only the opening crack. In the years that followed, more symmetries connected to the weak force started to fall apart, one after another. And this is the thread that eventually leads us towards solving the riddle of matter and antimatter. Physicists realized they could patch things up in the Wu experiment if they combined the mirror flip with a second transformation, swapping every particle for its antiparticle equivalent. That process is called charge conjugation. Do both flips together, mirror reflection plus particle to antiparticle swap, and suddenly the scenario with a counterclockwise spinning antineutrino becomes something that could actually exist in our universe. This joint operation earned the name charge parity symmetry, or simply CP, referring to charge and parity combined. So even though the weak force clearly disregarded plane parity on its own, maybe it would still respect this combined version. That hope didn't survive long. A fresh round of experiments soon revealed that CP symmetry also fails, and the culprit this time was a strange little particle called the kaon. Kaons belong to a family called mesons, built from one quark paired with one antiquark. The neutral kaon, the version carrying no electric charge, is made from a strange quark and a down quark. But there's a twist. There are actually two distinct neutral kaons, one pairing a strange quark with an anti-down quark, and another pairing an anti-strange quark with a regular down quark. Because of this odd setup, the two neutral kaons can flip back and forth into one another. So a stream of neutral kaons has to be treated as a genuine quantum blend of both possibilities at once. Kaons don't stick around long. They decay into lighter particles called pions after roughly a billionth of a second, and if both charge and parity together are conserved, that decay should always spit out 3 pions. In 1964, researchers set out to test whether this combined charge and parity symmetry actually held up. They sent a beam of kaons streaming down a long tube and tallied what came out the other end. The overwhelming majority of decays, 499 cases out of every 500, produced the expected burst of 3 pions. But one case in 500 broke the pattern, yielding just 2 pions instead. And there it was again, another crack in what physicists had assumed was an unbreakable rule. Charge and parity together were not being conserved after all in how kaons fell apart. That discovery earned Val Fitch and James Cronin the Nobel Prize in Physics in 1980, and it sent shockwaves through the physics community. But what does it actually mean for charge parity symmetry to break down? What does that tell us about the universe we actually live in? At its core, it reveals that the rules governing matter aren't identical to the rules governing antimatter. Remember that earlier thought experiment about two civilizations from different galaxies trying to figure out, before ever meeting face to face, whether they were built from matter or antimatter? This is finally where we get an answer. A neutral kaon has to be understood as a genuine quantum superposition of matter and antimatter simultaneously. Occasionally, that quantum mixture decays into an electron paired with its antimatter twin, the positron. If charge parity symmetry held perfectly, you'd expect those decays to churn out equal numbers of electrons and positrons. But once again, Cronin and Fitch found otherwise. For every 300 electrons produced through this decay, 301 positrons showed up instead. So if our hypothetical civilizations from opposite ends of the galaxy wanted to know, independently and without any prior contact, whether they were made of matter or antimatter, all they'd need to do is run their own version of the kaon decay experiment. That tiny asymmetry would tell them everything, and they'd finally know whether shaking hands across that vast gulf would be safe or catastrophic. Electromagnetic signals alone would never have revealed this difference. Conversations built around gravity or the strong nuclear force wouldn't have settled it either. But if that distant encounter ever happened, discussing experiments involving the weak nuclear force would finally give them something absolute, something with no ambiguity at all. Still, this raises an obvious question. Why does nature bother breaking symmetries that, on paper, seem so elegant and obvious? Life would arguably be simpler if matter and antimatter obeyed perfectly matched, perfectly balanced physical laws. And yet this particular violation, known as charge parity violation, turns out to be just the opening chapter. Its consequences ripple outward much further than anyone initially expected, shaping the universe on a much grander scale. To really make sense of that, we need to rewind all the way back to the earliest moments of existence, back to when the blazing chaos of the Big Bang somehow settled and locked into place. So why exactly did the universe freeze into the form we see today? What's the deepest ambition driving fundamental physics? Is it simply to catalog what everything is built from? Or is it to trace the universe back to its very first instant? For Einstein, even as he lay on his deathbed, the answer was straightforward. The greatest prize of all would be a theory of everything, a single framework capable of merging all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. That unification has long stood as the ultimate goal linking quantum mechanics with general relativity. Ever since Einstein wrestled with the problem in the early 1950s, physicists have made gradual progress. The weak force and electromagnetism were successfully merged during the 1960s. The strong nuclear force took considerably more effort, but eventually it too found its place within the framework known as quantum chromodynamics. The one piece still missing, the challenge that has occupied fundamental physics for well over a century, is folding gravity into that same picture, something physicists still haven't managed to pull off conclusively. So how exactly do physicists go about constructing these grand unifying theories in the first place? Once again, the guiding compass is the pursuit of symmetry and elegance. Some of the most important hints have come from smashing particles together at enormous energies. As those collision energies climb higher and higher, something strange starts happening to the fundamental forces themselves. They begin shedding their individual identities, changing the way they interact with matter, gradually losing what makes each of them distinct until, at high enough energies, they all start to resemble one another. Take a look at electromagnetism and the weak force as they behave in today's universe, and you'd swear they belong to entirely different categories. Electromagnetism binds charged particles together, while the weak force drives a kind of radioactive decay. On top of that, electromagnetism travels through space via the photon, a particle with zero mass, while the weak force relies on three hefty carriers, the neutral Z particle, along with the positive and negative W particles. Yet push the energy high enough, and that sharp boundary starts to dissolve. Physicists call this the electroweak theory, and it tells us that what looks like two separate forces is actually one and the same force once conditions get extreme enough. That means way back when the cosmos was young and blisteringly hot, there was no split at all, just a single unified interaction. It was only as the universe expanded and cooled down after the Big Bang that this symmetry cracked, splitting one force into the two we observe now. Crank the temperature up even further, and the line separating the electroweak force from the strong nuclear force starts to fade too. Go further still, into truly extreme heat, and even gravity is thought to lose its distinct identity. Put all of that together, and it points towards something remarkable. At the very moment the universe came into being, there was just one force, sometimes called the superforce, and it was flawless in its symmetry. There's an odd echo here with the opening line of Genesis, the one about the Word existing before anything else, existing as pure and divine completeness. The biblical narrative starts with a state of perfection that later becomes flawed. Modern cosmology tells a strikingly similar story. At the very start, everything was symmetrical and whole. That single superforce ruled over all of existence, unchallenged. But as this scorching universe stretched outward and cooled, cracks began forming in that once perfect symmetry. Flaws emerged where there had been none. The forces peeled away from one another one at a time, gravity breaking off first, then the strong nuclear force following. As cooling continued, the weak force eventually split away from electromagnetism as well. None of these splits happened quietly. Each time a force broke away as the universe cooled, the fundamental character of the cosmos shifted. Before and after each break, the universe was a genuinely different place, having gone through what's called a phase transition. Think of water turning to ice as it cools. The liquid has a certain symmetry that the solid ice doesn't share anymore. In much the same way, every time a fundamental force separated out, it marked a real fracture in the underlying symmetry of the universe. And cosmologists suspect these fractures shaped some of the most important features of the reality we now inhabit. Gravity's departure happened at what's called the Planck time, when the universe was roughly 10 to the negative 43rd power of a second old, an unimaginably brief instant. We understand almost nothing about the universe at that age, and until physicists managed to construct a genuine unified theory bridging quantum mechanics and gravity, that era may stay permanently out of reach. The strong force's departure is a different story, though. It happened later, somewhere around 10 to the negative 34th power of a second after the beginning. And this is a period that physicists feel they have a much firmer grip on, because it lines up closely with the moment cosmic inflation blew the universe outward. Tags follow the required 2-punctuation rhythm, with paragraph opening tags and at least 45 characters between consecutive tag starts. Back in the late 1970s, a physicist named Alan Guth found himself troubled by a puzzle about the cosmos. He'd built his early career in particle physics, chasing after grand unified theories that might explain everything in one elegant package, all while also chasing something more mundane, a stable academic job. Then, in 1978, he sat in on a lecture that reshaped his entire path. The speaker was Robert Dicke, a senior and widely respected figure in the field. Dicke, much further along in his career than Guth, had spent years probing cosmic mysteries, and in this particular talk he raised the question of why the universe looks flat rather than curved, like the surface of a sphere or a saddle shape. Somehow, he argued, the birth of the universe must have been tuned with remarkable precision to land on flatness out of every possible geometric outcome. That idea stuck with Guth. He started wondering whether this apparent fine-tuning connected to another oddity, the fact that a certain kind of particle seemed to be conspicuously missing from the universe, a particle whose existence was also predicted by symmetry arguments. The reasoning traced back to James Clerk Maxwell's work on electricity and magnetism. His famous equations were strangely lopsided, describing electric charges in detail, but offering no true magnetic counterpart. Every magnet we encounter comes with both a north and a south pole bundled together, forming what's called a duopole. Long before Guth came along, other physicists had already been asking where these theoretical magnetic monopoles, isolated north or south poles standing entirely on their own, might be hiding. Guth's answer was that they must be tucked away somewhere we can't easily see. He proposed that in the universe's earliest, hottest, most chaotic moments, electromagnetism was fully symmetric, and magnetic monopoles existed as an ordinary part of the mix of particles filling space. But then the universe underwent an extraordinary burst of expansion, doubling in size roughly 80 times in an almost unimaginably short span. That expansion spread the magnetic monopoles out so thoroughly that only about one would remain within our entire observable universe. Once this era of inflation finished, there simply wasn't enough leftover energy to manufacture any new monopoles. They were essentially erased from existence, destined never to show up in any physics experiment. So what exactly happened to the universe while it was expanding so violently? A background energy field known as the inflaton must have taken over, dominating everything. The overall density of the universe plummeted as ordinary particles were stripped of their energy almost entirely, leaving behind a cold, nearly empty void. Yet space itself kept churning, and eventually the inflaton field decayed, bringing inflation to a close. All that stored energy got released back into the universe in one dramatic reheating event, driving temperatures up to billions of degrees and generating the matter that fills the cosmos today. The magnetic monopoles, though, never came back. Curiously, this entire sequence unfolded around the same moment as another phase transition, the separation of the strong nuclear force. Was that timing just a coincidence? Or did the strong force's departure somehow inject the energy that powered the inflaton field? Nobody knows for certain. Our understanding of the physics governing this era still has real gaps, which means we can't say with confidence that we've identified the actual trigger behind inflation. Some researchers have tried linking the inflaton to the Higgs field, the field responsible for giving particles their mass, while others have speculated that the inflaton might simply be an earlier version of what we now call dark energy. By the time the universe reached about 10 to the negative 12th power of a second in age, sitting at a temperature near 10 to the 15th power in Kelvin, Every one of the fundamental forces had finished splitting apart into the distinct forms we recognize today, but symmetry breaking wasn't quite finished with its work. This was also the era when a process called baryogenesis took place. This marks the point when the churning mixture of fundamental particles, the quarks and gluons, started coalescing into protons and neutrons, giving rise at last to the ordinary matter that makes up you, me, and everything else we can touch. Yet a nagging asymmetry remained unresolved. Recall that the energy released by the decaying inflaton field is what ultimately populated the universe with matter and light. Logically, that reheating process should have created equal amounts of matter and antimatter. And yet one of the most glaring imbalances we see in today's universe is just how heavily matter outweighs antimatter. Every survey of the cosmos turns up abundant matter and only faint traces of antimatter. To put a number on it, scientists estimate that within our own Milky Way galaxy, there's roughly 1 part antimatter for every quadrillion parts of ordinary matter. So where along the universe's timeline did this imbalance take root? Why does matter so overwhelmingly outnumber its antimatter counterpart? The leading suspicion is that the answer lies somewhere within the details of baryogenesis itself. We do know that the laws of physics treat matter and antimatter slightly differently. That much has been confirmed experimentally. The trouble is that this known difference is far too small to explain the overwhelming dominance of matter that we actually observe, which leaves physicists still digging into the fundamental rules governing the universe, trying to figure out why there's any matter left over at all. There's a strange way to measure just how lopsided matter and antimatter really were in the early universe, and it comes from something you wouldn't expect: the cosmic microwave background. Those photons trace back to the moment when matter and antimatter across the cosmos finally wiped each other out. And here's the striking part. For every single proton or neutron that exists today, there are roughly 1 billion of these leftover background photons drifting through space. What that tells us is that the early universe must have been almost perfectly balanced between matter and antimatter, but not quite. For every billion particles of antimatter, there was 1 extra particle of matter, 1,000,000,001 instead of an even billion. That razor-thin surplus is the reason anything with mass exists at all today. Every star, every planet, every one of us, all traces back to that sliver of imbalance. It's a humbling thought, honestly, that our entire existence hinges on such a tiny crack in an otherwise even split. Even so, there's one more mystery that symmetry might still be hiding. If nature really does follow symmetry all the way down, and if the fundamental laws of physics are truly symmetric at their core, then magnetic monopoles shouldn't be the only exotic things waiting to be found out there. Take supersymmetric theories as an example. In that framework, every quark should have a mirror partner called a squark, and every electron should be paired with something called a selectron. This pattern of naming keeps going across the entire standard model. Neutrinos get partnered with sneutrinos, muons with smuons, and on the boson side, Higgs bosons pair up with Higgsinos, and photons with photinos. If this is right, there's an entire shadow universe of supersymmetric particles sitting just beyond what we can currently detect. Supersymmetry sits at the heart of a lot of proposed theories of everything, and for years, physicists genuinely expected the Large Hadron Collider to turn up solid evidence for it. But every search for these elusive partner particles inside our colliders has come back empty-handed. What we keep finding over and over are the same familiar particles we already know: ordinary quarks and electrons, nothing more exotic than that. Some physicists now argue that leaning so heavily on symmetry has actually misled us, that we've been following the wrong thread all along. Others simply find the idea too compelling to abandon, so the search for supersymmetry, and for some deeper unifying force behind it, keeps going. We're nearing the end of this exploration, and if there's one thing that's become clear, it's that symmetry sits at the very core of how we understand the universe. But strangely enough, it's the breaking of that symmetry that gives the cosmos its character, its quirks, its personality. The laws of physics as we know them, and the very existence of matter itself, both emerge from flaws, from cracks in what would otherwise be a perfect, featureless universe. Before wrapping up this train of thought, though, there's one more angle worth considering. It's easy to think of symmetry breaking as something that belongs entirely to the ancient past, a series of events locked away billions of years ago. But our universe hasn't stopped. It's still expanding, still cooling, still shifting in ways we can barely track, and we're standing at just the earliest moments of an unimaginably long future still ahead of us. Somewhere below the energy levels our experiments can currently probe, there could be entirely new symmetries waiting, ones we haven't even theorized yet. And as the cosmos keeps cooling over unimaginable stretches of time, those hidden symmetries might eventually crack too, splitting apart and releasing forces and phases of matter we can't yet imagine, phenomena that could reshape the universe in ways just as dramatic as anything that came before. The universe's long slide from a state of perfect symmetry into this messy, broken, structured reality we live in might still be far from finished.